ones I listed is Daniel Leo. He is interviewing for our inorganic faculty position here. He comes to us from the University of Nevada for your associate research professor.
I just finished up the professorship there.
Professorship?
Yeah.
And you got your PhD in inorganic chemistry from the University of California, right?
Yes.
And it was in lanthanide production chemistry.
Yes.
Okay, and you also got your BS degree from the University of California.
UCLA, yes.
Okay, so welcome here and look forward to listening to you talk.
Well, good afternoon, and let me just perfectly apologize if I occasionally cough. Came off a bad cold last week and still been raining, so if I cough, I do preemptively apologize for that. So as mentioned, I'm going to be talking about some F element chemistry and some related chemistry to that. And this is based on research I've done both at the University of California, Irvine and University of Nevada, Las Vegas.
So it's not making it like go forward either?
There we go.
Okay.
All right.
It's not working.
So I'm basically going to be breaking this up into three separate areas. A little bit of background with the F elements and some of the methods that I've used with air washes and chemistry. And I'm not really sure how many of the undergrads here, it looks like there's at least a few. So I don't know how much you really know about MR or X-ray diffractometry. I'm not really going to go into too much depth there, but I'm just going to cover briefly what they can show us. And I'm going to talk about two projects which I've done, one more on the molecular level, one more on more of a material synthesis. And then talk about two projects which I've done with undergraduates at UNLV. There we go. So when most people think of the periodic table, this is pretty much all they think of. And they kind of don't notice that there's nothing, that there's something that's written down here. And a lot of chemistry textbooks in the past and a lot of inorganic chemists kind of felt that, there's nothing really interesting about it, they're boring, they're all alike, so man, why even bother thinking about these? But I, as well as certain other people, would disagree. And I want to kind of show here how the F elements are a little bit more diverse, a little bit more interesting, and kind of an unexplored area relative to most of the rest of the periodic table. So the F elements comprise of two series, the lanthanide series, which are also known as the rare earth elements, and the actinide series, which contains thorium, uranium, plutonium, and other fun things to play around with. Now, these are called the F elements because their frontier orbitals are the F orbitals. So you have an element like carbon, which has P and S orbitals. Then you have the transition metals, which all have D orbitals as their frontier orbitals. Well, lanthanides have the F orbitals, thus they're known as the F block or the F elements. Now, with the lanthanides, there are three main features that you need to keep in mind. First, there's a limited extension of these F orbitals, the presence of what is known as the lanthanide contraction, and the stability of the 3+ oxidation state. So, interesting thing about the F orbitals, especially in the lanthanides, as well as the later actinides, is that the orbitals are actually so tightly held, they're actually, within the noble gas xenon core. So with lanthanum, it's a 3+, D0, S0, basically xenon core. And as we go along to each succeeding elements, it doesn't really matter how many electrons you add, they're all being added to the F orbitals, and because they're so tightly held and not really interacting, they just sit there. So this can have up to 7 unpaired electrons. with gadolinium, and they just don't otherwise interact, which is why they're often used for permanent magnets, because it doesn't really matter what chemical environment they are, unpaired electrons, unpaired electrons, and they're just not interacting. But as a consequence of that, all the lanthanides tend to be 3+, with no interaction, and they're all 3+. It would seem that they're pretty much all the same, and throughout history it's kind of been difficult to separate them out, or even identify them from each other. So 3+ for all of them is the default state. You can get 4+ for some of these, and actually 2+ for many of them, and recently 2+ for all of them. But it's very, very unstable, and 3 is the preferred oxidation state. Which means that the lanthanide contraction plays a key importance in the chemistry of the lanthanides. So as you go along the series, lanthanum, cerium, residium, and so on to lutetium, I also included yttrium here. This is actually a D element, but it's 3+ and similar size to holmium, and it's often just treated as another rare earth or lanthanide element for all intents and purposes. But because of this contraction, you have a very gradual and very regular decrease in the ionic gradients. And this can have an effect on reactivity. So, for example, this is a tris pentamethyl cyclopentadienyl compound. Around the lanthanide, this is 3+. Each one of these ligands is 1-. This is a very asterically oversaturated molecule, kind of hard to get these 3 bulky rings all around the metal. There are 2 methods of synthesizing this, well, more than 2, but just 2, for example, here. One, you're basically replacing this tetraphenyl borate with a pentamethyl cyclopentadienyl from a potassium salt, or alternatively, you can start with hydride, to add the hydride to this organic fragment to form a pentamethyl cyclopentadienyl, thus forcing it to coordinate. For the relatively large samarium, both of these methods work perfectly fine. When you get to something the size of lutetium, basically this doesn't really work. This is just too sterically hindered. Now it starts working. This is just too sterically hindered, so this won't form. But this method kind of forces it to, so you can hand get lutetium compound through that method. Lutetium, which is the smallest of the lanthanides, it just won't work. It's just too crowded. It just not enough room. So that slight change in ionic gradients completely changes the reactivity. So I'd just like to mention a couple of methods that I use to work with some of my air and water sensitive chemistry. The 2 main pieces of equipment I use is a Schlenk line and a glove box. The Schlenk line is a dual inert gas and vacuum manifold. Basically allows you to attach a vessel, solution, whatever, and you can pull vacuum, replace the air with inert gas. In this case, I'm using argon, and do that repeatedly, and you can establish and maintain an inert atmosphere and keep out air and water. So looking a little bit closer, and I have vacuum running through the line in the back, argon, inert gas in the front, and I can basically switch back and forth with this valve. Glove box is basically an enclosed, sealed environment. You have, of course, that allow you to, again, vacuum inert gas to establish inert atmosphere and bring things in or out. And this has an active catalyst down here that will actively strip the atmosphere of moisture and oxygen. Just an example of how well this works. This is a reduced titanium compound. This is a 3+ titanium complex, nice, beautiful emerald green, sitting in the glove box. I just leave this open, soften that way, so I get beautiful green crystals if I do it right. And it'll even just sit there, no air and water to oxidize it. As soon as I take it out, I mean literally within seconds, it just material crashes out, it oxidizes, turns dirty brown red. So you can actually maintain these beautiful chemicals, very expensive chemicals, either in a glove box or in a Schlenk line. And finally, at my background, I just want to quickly mention NMR and X-ray diffract compound. I'm not really going to go into the theory behind it, but the basic idea with nuclear magnetic resonance spectroscopy is that different nuclei will absorb electromagnetic radiation at different frequencies. So carbon-13 different from fluorine-19 from lead-207. Furthermore, the exact frequency is actually dependent on the chemical nature of the particular nucleus. So, for example, a hydrogen that you pick up around 7 ppm on the scale, you know, is probably going to be one of these aromatic rings, while something down here around 1 is going to be more of an aliphatic carbon simple alkyl chain. So based on where these are and other factors, splitting, coupling, etc., you can actually kind of build back exactly what your molecule is, which is important not only for organic, but also organometallic compounds, which have a lot of these types of fragments basically just stuck on there. Now with X-ray diffraction, basically you have a certain compound. This is a cerium dinitrogen compound. And you have a bunch of these the same configuration, all stacked together in the same orientation, just similar blocks all stacked together. And it forms beautiful crystals. And what you can do, because these are all stacked together and the same way, you can actually diffract X-rays through the crystal, and you end up getting these patterns and concentration of the diffraction into certain diffraction patterns. And if you take a lot of these patterns from a lot of different angles of the crystal, you can actually back calculate what this structure is. And this structure is actually determined from a bunch of pictures like this. So this is actually calculated, and these are where they're located, angles, and you'll notice that some of these are kind of larger than the others. These are ellipsoids, and these are drawn about 50% probability. So 50% of the time they're within the ellipsoids. So the central matter is kind of heavy, easy to detect, really small, while the larger ones, which can kind of flop around a little bit, are much larger ellipsoids. So the first project I'd like to talk about is reduction of dinitrogen with lanthanides. This is a samarium-2 compound. So I said before that samarium-3 is the most common, but you can get divalent species, and this is one of the divalent species. Again, this is a monoionic pentamethyl pentadienol. It turns out that this compound will reversibly bind dinitrogen, so as you lower the temperature, you end up getting more of this structure here. Now, if there was oxygen present, the oxygen would just immediately rip this to shreds, and that would be done with it. So this is a reaction done in an air-water free environment. And one way I kind of probed this reaction was looking at the NMR of nitrogen. So carbon and proton are the most common, but you can do other nuclei, and one nuclei I've used is nitrogen-15. So this is the nitrogen-15 spectrum at room temperature at top here, and this peak here is free dinitrogen. And as I lower the temperature down to eventually 203 degrees Kelvin, I see some shift in that and how it disappears. But at the same time, I see a new peak come in and shift, with which is relatively broad and indicative of the formation of this compound. So at room temperature, I have primarily this. As I go down, I eat up the free dinitrogen and are forming this dinitrogen complex. It turns out that with more powerfully reducing lanthanides, they will irreversibly bind. So for example, a divalent lanthanide diiodide with potassium salt of a bis-trimethylsilylamide, this ligand here, under dinitrogen will form a dinitrogen complex, and you're basically looking at potassium and iodide by forming a lanthanide amide bond. And it turns out you don't really need a divalent starting material. They're kind of pain to make, and at the time you just couldn't get it for most of the lanthanides. Start with a trivalent. This is a 3+ tris-trimethylsilylamide, And here I use potassium graphite, basically dissolve potassium onto graphite. It helps disperse the potassium, allows it to react a lot more efficiently. So the potassium oxidizes from 0 to +1, reducing the lamp nitrogen +3 to +2, and then that reduces the dinitrogen to form this compound. Now at the time I was doing this, only 6 of the lanthanides had known divalent starting materials or accessible states. It turns out that you can do almost all the smaller lanthanides, even ones such as gadolinium and terbium, which shouldn't be able to be reduced by sodium, yet demonstratively I could. And here's again the thermal ellipsoid plot, which is what this is called, or crystal structure of the gadolinium dinitrogen complex. Here is this trimethylsilyl amide, and this is a tetrahydrofuran neutral ligand coordinating to the gadolinium to fill out its coordinations here. So I noticed I didn't mention the early lanthans, lanthanum, cerium, praseodymium, kind of question of whether we can make this or not. Turns out we couldn't isolate a crystal structure of this, and the reason was that we were actually getting this compound. This is actually overall an amide, so 3+ cerium for these this trimethylsilyl amides, which are 1- each, so overall 1-, and sodium as a countercation. What it turns out to be happening is as soon as we start forming this compound here, the byproduct is an alkali metal amide, and this is combining with the starting material to form these tetrakis anions. So because of that, we're eating up all these, the byproduct and starting material, so we're not really getting a lot of this. We are actually able to form this. We can see the signal, proton signal in the NMR, but we just have not been able to crystallize it with this ligand because this is just so large that it allows another amide in. The smaller lanthanides don't, which is why you don't form this and you end up getting a lot of this compound. Now we can get the larger ones by switching to a larger ligand. In this case, this is a tetramethyl tetramethylcyclodiol ligand, and it will form a dinitrogen complex. Here is a cerium dinitrogen complex with the tetramethyl CP ring. And we can also get this with the pentamethyl cyclopentadienyl complex. Here is, again, the serum example of the pentamethyl. And since I was able to get the N15 NMR with the samarium, which kind of took me all night and lowering rating the temperature, decided to find it for the cerium praseodymium. I was able to find it and notice that just that slight difference of a methyl group here or the lack of a methyl group on this entire structure can shift it so radically by 130 ppm. And here's the praseodymium example, both tetramethyl and the pentamethyl. The second project I wanted to talk about was the uranium nitride synthesis. So uranium nitride is being considered as a possible alternate nuke fuel for nuclear reactors to the currently used uranium oxide. And usually this has to be done by a very high temperature route, but I decided to try to do this in liquid ammonia, which at room temperature is a gas, and you kind of need to cool it to like 50, 60, minus 50, minus 60 degrees Celsius. And usually I've done this in a dry ice acetone bath. And a simple reaction I need is take a uranium tetrachloride, sodium amide, do a simple salt metathesis, so I lose sodium chloride, which is soluble in ammonia, and then insoluble uranium tetrakis amide, and then take this material, heat it under vacuum to convert it to the nitride while taking off ammonia. Now to do this, I actually invented this apparatus here. It's a dual Schlenk flask. So this is under a vacuum or argon on a Schlenk line. I have two of them set up, and they're only connected at the bottom by a glass filter for it. And basically what I can do is I can do the reaction here, and then filter it through here by simply twisting it while keeping the entire thing submerged safely in a cold bath, so I don't end up hitting a liquid next to a material which is tens and tens of degrees higher than its boiling point. It was just a question of safety. So by following this reaction in this exact same way, what I ended up getting was uranium oxide. Now this is what's known as powdered X-ray diffraction pattern. So rather than having a bunch of nice little dots and a single crystal, you have a bunch of small crystals all crushed up. So you don't get that nice pattern, but nonetheless, when you reflect off it, you're going to get certain angles that are going to reflect heavily, which is what we're seeing here, based on the overall angle of the beam and the detector. Interesting thing is that when I add a small amount of sodium metal to the ammonia, sodium metal being fully dissolvable in ammonia, I end up getting 73% uranium nitride. Add more, and I can get 90% uranium nitride. So just a small matter of adding sodium completely increases the yield from pretty much nothing to about 90% without changing anything else. Now I'd like to switch to a couple of projects I've done with undergrads. In this case, uranium lanthanide separations. So uranium in a nuclear reactor, hit it with a neutron and basically splits into two unequal nuclei. And this is a distribution chart of the masses that you usually see. So a heavier one, lighter one, yes, get energy, of course, and neutrons. But some of the fission products are the lanthanides, and they're kind of interest for forensic purposes. So if someone sets up a dirty bomb or whatever, a lot of lanthanides, the exact isotope composition can tell you what type of bomb it was, what the material was, and even what reactor it came from. I'm not producing that exact information, you kind of need higher clearance for that, but nonetheless, you can still develop the technique. And I look to separate the metals from each other using hexafluoral acetonate. This is a fluorinated ACAC. I'm just going to refer to HVAC. The protein is a very acidic, very volatile compound, and this ligand is actually pretty volatile in and of itself. And I've also used diaryl, which is basically polyether, to help coordinate around the metals, break up polymerization, and try to increase volatility. And this is the undergraduate that I was working with. So with uranium, add HHVAC to the oxide, you end up forming this uranyl species. So uranium double bonded, or some would say triple bonded oxygen, uranium, 2 HVACs, so this is uranium-6, with 1, 2, 3, 4, 5, 6 counter anion overall charge, and a neutral water coordinate. With lanthanide, again, predominantly 3+, I have 3 HVACs, and to complete the coordination sphere, I have a diagonal coordinated around here. This is the terbium example. So basically all I did is I took a mixture of uranium oxides and lanthanide oxides, in this case a trivalent oxide, tetravalent, and a mixed valent oxide, and mixed them in proportion to their fission yields from the electron reactor. In this case, it was about 50-to-1 ratio of uranium to the lanthanides. Use various salts to see which one would work best: ether, tetrahydrofuran, toluene nitrile, 2 concentrations of HVAC, enough to hypothetically react with all the oxides, or enough to react with just the lanthanides, both with and without diagonal room temperature and at reflux. It turns out that the one major factor that changes things is the solvent. So, for example, in toluene, I was actually getting massive preference for lanthanum over uranium. It preferred extracting the lanthanum over 400 times as much as uranium. So, even though the uranium is nearly 100 times as much as the lanthanum, I was actually getting more lanthanum in the extract than the uranium. While with other solvents such as CHF, that kind of reverses itself, and I'm actually preferentially extracting out the uranium. So simply by changing the solvent, I can completely change the profile of the extraction. So it's a very fine-tunable process here. And this was actually recently published in the Journal of Radioanalytical and Nuclear Chemistry. I should note that the cerium didn't really react at all, and the praseodymium was intermediate in reactivity between the lanthanum And since most lanthanides are form trivalent oxides, this would work well for the vast majority of the lanthanides. Second project I worked on involves lanthanide methacrylate. So this is methacrylic acid here, decarbonate, and you have a methacrylic methacrylate anion. This is done with a undergraduate at UNLV, and she's currently applying to various graduate schools named Sierra Mayor. And she did tremendous work on this, let me say. So basically, I form these infinite chains of lanthanide methacrylates. And I do this by adding the acid in water directly to a lanthanide carbonate. So basically, it reacts like vinegar and baking soda. Releases CO2, water, no other byproduct, very nice and clean. Now, for the early lanthanide, lanthanum through neodymium, I'm getting a 9-coordinate species and various coordinations of the methacrylate. So here I have methacrylate coordinated to just one lanthanide. And here I have a bridging, it's bridging through one oxygen and then through another, and this, we call this an 801 bridging mode. Here, on the other hand, it bridges through one, while the other oxygen bridges through two. This is known as 801, 802 bridging mode. And there's also some neutral waters coordinating to fill out the coordinations here. This is a crystal structure, ball and stick. Just give you another kind of representation of the infinite chain that I'm making. The undergraduate is working with Sierra. Was also managed to make this anhydrous compound. It's still a 9-coordinate lanthanum compound, but instead of waters, it has a actual methacrylic acid coordinating to allow it to keep coordination character. As we go down the periodic table, lanthanides get smaller. They can't handle 9 oxygens coordinating. So for middle lanthanides, we end up getting 8. In this case, we have bridging 801, 801, and a bridging 802, 801, 2 times over. This is another crystal structure example of the infinite chain, just a different view. For the late lanthanides, again, they're getting smaller. I can only fit 7 rounds over 7 coordinate, and the main difference between this and the previous one is one of the previously 802, 801s becomes purely 801, 801. Again, another view here. Now, if you were paying attention to your table, you notice I kind of left out holmium and erbium, and they're kind of stuck between the 8 and 7 coordinate. And it turns out that they're both. So in the crystal structure, we saw coordination of both 801, 801, this O2A, O1A, as well as an 802, 801, O2B, O1B. There's about a 3-to-1 ratio between them, which means half the time I had an 802, 801, and an 801, 801, and the other time an 802, 802, and 802, 802, which means that half the time is 7 coordinate, half the time is 8 coordinate. I did have some computational studies done on this with a coworker named Zinja Kim, and it turns out that the energy level between those two structures are pretty much the same. They're degenerate, so it's equally happy to be in each one. Neither one really fits perfectly well, so it sometimes does one, sometimes does the other, and basically tries to do the best it can. So basically, we see the lanthanide contraction in work going from a 9 coordinate to an 8 coordinate, which transitions to a 7 coordinate. And then just another view of the 9, 8, 7 coordinate, mixed coordinate, and this is actually computational structure for promethium, which we determined that the lowest level would be 9 coordinate rather than the 8 coordinate. So we can see 9 to 8, 8 to 7, with the variable holmium and erbium. Now, the undergrad is working with kind of on her own, did some work with the methacrylates with not only lanthanides, but also alkali metals thrown into its bimetallic. And she actually came out with this rather nice little synthesis here. She cooked this up in autoclave and nice, beautiful crystals. And some of these crystals you get like, centimeters long. really huge, beautiful ones. And this is crystal structure of one of these. It's really kind of busy. I actually use this occasionally as a background for my laptop and my home computer. But what we have here is we have a series of interlocked chains, basically these snake-shaped or sinusoidal chain here with neodymium, this dark green and bluish green being the sodium. We can kind of strip off some of the carbon and excess hydrogen. We can see overlapping chains, one on top of the other. And then above and below, same thing, where basically they're at 90 degrees, so here, 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 here. Now they're slightly more stripped down, so we have chains here, and then chains up and down here. So a bunch of chains going right to left, stacked on top of each other, and chains coming into and out of the board. And here's another view of the individual chains and how they're kind of connected, again excluding the carbons and hydrogens to kind of show you the overall connected backbone. And again, just another view of how they're connected and some of the differing coordination environments for the sodium, as well as the oxygen coordination sphere around the neodymium. Now, by switching from simply sodium to the larger potassium or rubidium, we got a really interesting compound. So from this angle, you see a bunch of this lonesome red dots sitting here. And basically these are waters that are trapped in pores. Now you'll notice that they're not really very close to a lot of metals, so they're not really coordinating. These metals are kind of just held in these pockets. Now if we look down, we can see the waters a little bit more clearly in these pores. Now these are not all in a plane, this is kind of looking down multiple layers as they stack up. A little closer up view to see the pockets. And here is a space filling model with the water smooth to show you where the voids are. We only got so far with these compounds, and there's still a lot to explore, and I would be kind of interested in looking to see what other type of structures we can get from this. So I hope I've shown you a variety of different chemistry with the F elements, from molecular to solid-state compounds to synthesis to separations. So a wide variety, and I think there's plenty more open to explore. This is just a small fraction that I could include in the time allotted. And one of the things I'm kind of interested in looking at, down the road and something to build up on is not just molecular to materials, but molecular and materials, trying to bridge the gap between classical coordination chemistry and surface resin chemistry, or basically combining blending organic metallic chemistry with solid-state and polymer chemistry. So, for example, taking a polymer chain and basically attaching the ligands, instead of having them freely floating around in solution, I can have them firmly attached to a polymer resin. And based on that, I can do the chemistry here, attach whatever metal I want, do the chemistry there, and basically flush out whatever it is I've used it for, small molecule activation, polymerization, whatever. Here's an example of discriminating between trivalent and a divalent, where this would deprotonate a proteo version of this and attach, while a divalent doesn't have that to react with. Well, I mean, it would provide a way of kind of really concentrating your material. So if you have something that's really expensive metal or poisonous metal, you can help keep it all intact, all together, very little danger of contamination. So in summary, I hope I've shown how the wide range of F element chemistry, going from molecular to materials chemistry, shown the utility of air and water sensitive chemistry. This is the type of chemistry which even undergrads have done. I've had several undergrads that actually worked in glove box, on a schrank line, on vacuum lines. So this is something that is easily learnable and just isn't really as widely taught as it should be. As well as demonstrated how undergraduates have successfully published in peer-reviewed journal and also appeared in international conferences AXOR, Rare Earth Research Conference, Plutonium Futures, for example, and also how this can potentially unleash the potential of students. A lot of the undergrads I work with have gone on to graduate school. They've asked me for a letter of recommendation, and I've happily given very praising ones, because honestly, they did a great job, and they deserve a lot of the credit for those last two projects. So I'd just like to acknowledge some people who work at UCI, UNLV, and other collaborators, in particular my postdoc and graduate advisor, Bill Evans and Ken Stravinsky, so as the support staff to help keep us safe, including Dr. Tom Ledoux, crystallographers, various other collaborators, both national and international, computational chemists, spectrometry mass specialists, and very especially the undergraduates which I've worked with at UNLV. Any questions?
I'll start with my bet one. Lutetium and lawrencium are not actinized. They are S2F14D1. They perfectly belong in the slots where lanthanum and actinium are misplaced in periodic tables.
Well, regardless of whether one thinks lanthanum should go there or lutetium,
that was for the benefit of those guys in the back.
I mean, you'll notice also included yttrium, so if they're not, formally a lanthanized compared to a transition metal, I consider them honorary lanthanized, and will refer to them as such.
In the case of attaching the moieties to the resins, are you imagining these things being completely exchangeable and flushable the way we do ordinary exchange resins when you grab onto these?
To the metals?
To the metals?
Well, potentially. I mean, for example, I had a potassium salt up there, and I could imagine instead of doing the salt metathesis reaction and adding in a lanthanide. Alternatively, maybe the metal that I'm bonding it with is the end result I want, and I want to keep it firmly affixed. So a transition metal, for example, that binds to it would bind relatively strongly, similar to ferrocene. And I would use basically that as a solid surface to do reaction chemistry on, but instead of like a single salt, a more complex polymer resin technique. I mean, there are a lot of variations I could do and a lot of things to explore. This is just an example of a possible way forward.
Do you think the attachment chemistry, that is the ability to graft on these things to a presumably commercial polymer resin, that could be challenging?
I mean, it kind of depends exactly what the polymer you want. For example, when I had this one, that one, basically polyvinyl chloride and Grignard. It's a simple standard Grignard reaction. Basically, I'm attaching two organic hunks to each other and salting out the magnesium chloride. So something like that would be a little bit more straightforward, and it doesn't have to be a CP compound. I've made Grignards of Angus Woodruff on a house bases, and other similar type of organic fragments are possible as well. I just point that as probably as one of the more common classical organometallic ligands.
Speaking of CP ligands, I don't think we have to go back all the way to the slide, because it would be quite a way, but it's an early slide. In the reaction of forming the dinitrogen complex from samarium, bis-phenol samarium 2, you showed the samarium 2 complex as having the rings like so.
Right.
Is that real? And it's still
yes, it is real. And it's kind of attributed to polarization. So you have a 2+ sphere. You have a minus CP on there, and that kind of polarizes the metal. So the area close to the CP ring is slightly more positively charged in the area opposite of it. So that other CP ring wants a more negatively charged area and will kind of creep up until they bump into each other. So that's an actual crystal structure. So there's an actual crystal structure of that, and that is exactly what it looks like.
Okay. You don't see that with the transition metals.
You can for the earlier ones, which are similar, basically D0 type compounds. But yeah, that's basically due to polarization, and surprisingly enough, it is very real.
Another naive question. I asked this question without prejudice, but I did notice that you used the Eta nomenclature to designate attached atoms. Back when I was in the game, I remember that nomenclature started with attached carbons, and there was a considerable body of opinion that maintained that it should be only used for attached carbons and never for oxygens, nitrogens, or other heteroatoms. So my question is, has that been resolved one way or the other, or
I've seen this quite commonly used.
Okay, I guess that.
I've always seen it used. I've seen they've used like kappa instead of eta for a little bit more specificity for the connectivity, but for a simple connectivity like that, that's the eta type of nomenclature works perfectly fine, and I've seen it quite often.
More or less standard nomenclature nowadays.
More or less. I mean, some people prefer the kappa, which is a little bit more specific, but it's not to say this is somehow incorrect or unused.
Interesting how that's developed, because I remember there were some very strong opinions expressed back in the day. One other question, I guess, nobody else has one. The disorder structure that you showed.
Which disorder?
Not only remember one, but maybe I was looking at her. The one that was disordered between,
right?
We'll say Eta 7 and Eta 8, I think it was.
Yeah.
Is that's really disordered, and the reason I asked the question is I think you showed a crystal of that same compound.
I didn't show a crystal of this specific one.
Okay.
But yeah, basically in
in
the crystal structure, we actually located electron density, which is what you're actually measuring with the XRD, at both in both this conformation, the O2A O1A, and O2B O1B.
Well, maybe I conflated the structure with the crystal, but I couldn't help noticing that crystal looked exactly like a system that let's just say I know about it, in which it's a twin structure. And of course, twinning and disorder can look a lot alike sometimes. So I wondered if you had thought about that, if there was a way to distinguish.
Well, I mean, there might be a possibility where you just have a single infinite chain of pure 8-coordinate and a pure chain of pure 7-coordinate. But I could talk to our computational chemist, and just a random disorder would kind of, just according to them at least, make most sense. In the sense, it's really kind of right there between a pure 8-coordinate and a pure 7-coordinate. You can see how it kind of slip between the two.
Right. Yeah, exactly. That happens all the time.
But regardless of whether it's in the same, all the same chain, or just different chains, or differing within the one, we're still seeing both coordination modes in the same overall structure.
This isn't a subject I know a huge amount about, but my understanding is that twinning will often show up as falsely high symmetry and poor refinement of the structure.
Well,
whereas disorder will.
Well, at
show up
first,
as-
we kind of thought that was happening because this wasn't really, we weren't really getting good R numbers out of it. So the more and more results, the more we actually, turns out that we were seeing both electron densities. So it looked, so it pretty much the more we worked on it, looked that, yeah, it's not just, spread all over the place, we're actually seeing it in two separate locations in the same crystal. But a little bit more interesting in regards to that question, and I didn't really mention because I didn't really think I had time at the beginning, but you'll notice that with the samarium compound I have here, that I still list nitrogen as being
That's the slide.
3 bonded, even though I said it's reduced and this is 3+. Well, it turns out in the crystal structure, this nitrogen-nitrogen bond was about 1 angstrom, which is actually a little bit shorter than free dinitrogen. And N2 with 2 additional electrons should have a bond order of 2, come out to around 1.25 angstroms. What I think turned out is that we actually occasionally had we actually had normal 1.25 distance, but we also had slight impurity of oxides and oxygen here. And it is known that a slight impurity can give an anomalously short bond distance. There's an infamous case called the bond stretch isomer when they had 2 different colored crystals. They seem the same except the chloride seemed to be at 2 different distances. It turned out that some of the time that chloride was actually something else that was much shorter, and simply because the chloride is there most of the time, it resolved as a chloride, but at a shorter distance. So this crystal was actually kind of proof of that, the type of slight impurity giving you an anomalously short bond distance. And I've actually seen this in other compounds, not as well as carbon-carbon distances as well.
So X-ray crystallography can be a sporting method.
I mean, regardless of the method, you kind of need to understand what you can get. You kind of need to, if you will, grok the chemistry to understand, does this result make sense, or is there something screwy going on? Just because the computer says this is what it is, doesn't mean the computer isn't lying to you.
The uranium compound the undergraduate was working with, were there any special precautions that needed to be considered for the undergraduate to work with that? I mean, it sounds like, oh my gosh, radioactivity,
Yeah, and there was, of course, additional safety training and all that. Uranium, at least for amongst radioactive compounds, is not probably the most dangerous. I mean, your body will flush it out pretty easily. That being said, you don't want to start guzzling solutions of uranium. The main precaution was whenever we were handling the powders, the uranium oxide, we handled that inside a HEPA filtered fume hood. So when we weighed out, we would pre-weigh out a vial, add material, close the vial, carry it over in a secondary container to the balance, weigh that out until we got the correct amount, and usually weigh that first and then weigh everything else out around that.
so the undergraduate would actually wear a radiation badge and there'd be radiation monitoring or
Yeah, so basically in the lab that we're working in, we all had a dosimetry badge. When we were working with loose powder, even though it was in a fume hood, we had additional air monitoring to make sure that no free particles kind of flew out if the hood were to die or something along those lines.
Right.
But once it's in solution, the rating is sufficiently low enough radioactivity that you can just handle normal, gloves, normal hazard awareness.
All right, thanks.
I mean, the chemical nastiness, if you get it, is going to be more dangerous than the radioactivity. So just as long as you apply common sense and common radioactive awareness and procedures, for the most part, you're going to be fine.
All right, fair enough.
Interestingly enough, thorium, which actually has a shorter half-life than uranium, is a lot more dangerous because that's actually retained in the body at a high level. While uranium, again, it just flushes it out. And it's also one of the things where you have to, at UNLV, we had to give biological samples monitored. We had had any uptick, and it was kind of important for people to get base temps before they started working, because Las Vegas Valley actually naturally has a lot of uranium in the groundwater. And we kind of had an incident once where a couple of people who were born and raised in the area had elevated levels that were about the danger level. So after excluding all the possibilities and realizing that there's just a natural background there, kind of started doing a baseline to calibrate against everything else. It was a natural U-238 Durastane. Again, not super dangerous, but clearly not something you want to let go unmonitored.
It almost sounds as though that's an unfortunate place to do this kind of training. Did you start closer to it? As long as we're talking about coordination disorder, no, it's not the same kind of disorder, but do you ever see any disordered solids formed with these things, that is glassy solids?
Quite often. When I mentioned extraction with lanthanides from uranium, I've also done with other metals, including alkaline earth metals, for example. And especially when you have a lot of different metals in there, and also metals of the same column, so like rubidium, cesium, strontium, barium, similar chemistry, slightly different size, you end up getting very amorphous. So it looks like a nice crystal that's just too massively disordered. And sometimes you'll get degradation of products and a whole field of things. And I usually don't focus so much on that as the pretty crystals. I can put it on a diffractometer, get a pretty picture, and put into a pretty publication.
The theoretical chemist didn't think about glass transitions a lot, so that's why I raised it.
Yeah, a question that's not related to any of this, but are you familiar, when you said like dirty bomb and they can track back what reactor it came from? If you get poisoned with something that's radioactive, like that Russian, I don't know if you're familiar, a few years back. There was
It was with polonium.
Polonium, and they thought that, Putin was...
Yeah, well, I mean, that's just like a single isotope. With lanthanides, you actually get lanthanums, cerium, europium, promethium. Lanthanides have a plethora of, most half of them have a plethora of stable isotopes. So it kind of goes from plethora to 1 to bunch to 0 in the case of promethium. And obviously with fission, you're going to get a lot of radioactive ones, but you're going to get a wide variety of isotopes amongst the lanthanides. And the signature of what isotopes you get is actually very specific, not only to where the material came from, but exactly what it was comprised in it, and also the bomb design. Apparently you can do that. Again, I haven't been told all the dirty little secrets on exactly how you can calculate that, but that is an area of interest for forensics.
So they definitely could probably determine that it was a Russian someone.
Well, they can say it's a certain design that the Russians used or came from a Russian reactor, and there may be attempts at spoofing, mixing in different isotopes to fake it, but I know that that's one of those things that national labs are kind of working on tweaking and dealing with, and other high-level stuff that I don't know the details of, just that they're doing.
Don't become an enemy of Putin. Thank you. Any more questions?
No?
Thank you.